Hello, I welcome you all to this another interesting screencast where we're going to be solving this engineering mechanics problem, and it reads replace the loading system by an equivalent resultant force and couple moment acting at point A. This problem is coming from the engineering mechanics statics textbook 13th edition by R.C. Hibbeler. So we have been asked to replace the loading system by an equivalent resultant force and a couple moment acting at point A. So our reference point is A. So before I solve this particular problem, I'll just need to give an example of a very short problem so that we run quickly in this particular problem. So imagine you have a beam like so, and let's say this point is A, and let's say you have a force at this point B. At point B, you have a force system. Okay, let me just say, let's say I have a force system at this point like so. Let's say this is 5 pounds, so keep the same units, and let's say this is 10 pounds. Right, so imagine we are being asked to replace the loading system by an equivalent force and couple moment at A for this particular problem. This is what I want to explain, and this is what we're going to do in the other problem. So ideally what we need to do is to rewrite these particular forces about at point A and about point A for a moment. And what we need to do, let's say for this, let's call this as our force 1, and we call this as force 2. So for force 1, ideally what we want to do is, if we were to write force 1 as an equivalent force and result at couple moment at point A, then what we are doing ideally is writing this force here like this. We write 5 pounds, and we write another force like this, 5 pounds. So look at this. We've added a force, one positive, one negative at the same point. We can ideally say we've not done anything because 5 and 5 at point A can cancel out, right? It can. Okay, but I'll explain further. Let's write force 2 also. So this one was force 1. We've written it like this. Let's write force 2, okay, at point A. Okay, we are also going to do the same. So we can write this in blue like this. This is our force 2 equal to 10, and we can write another force at A in the opposite direction, so that again this is as if we have not done anything because the two forces can cancel each other. Okay. Like that. So this is what we've done. This is what we've done. So now let's go back to force 1. So what we are saying is, for force 1, this can be simplified further to a structure like this. Let me redraw this. So for force 1, look at force 1. This particular force, this one here at the bottom, and this one here, what do you think it's going to create? It's going to create a couple, right? A couple moment. We know what a couple moment is, right? A couple moment is a moment that is produced by two non-linear parallel forces whose magnitudes are equal, right? And it is a free vector, and by this we mean the rotational effect on, in this case, this beam AB remains the same, regardless of the position of the couple moment. Okay. So we are saying a couple moment is a moment that is produced by two nonlinear parallel forces whose magnitudes are equal, and the two forces are separated by a perpendicular are separated by a perpendicular distance between them. So let's say this is 5 feet, and then from there to B is 10 feet. Let me write this properly so that we finalize this particular problem properly. Okay, so we do this like so up to there. So we are saying like this, and then we have this distance here up to there like that. So we are saying this is 5 feet, and then this is 10 feet. So we are saying we are going to have a couple moment due to this 5 and the other 5 in the opposite direction, right? A couple moment. Okay, and we want that couple moment to be rewritten at A. Okay, because we know a couple moment is a free moment, a free vector. So if we are to do so, then we can do something like this. So we have a couple moment there, and then so if we are to write this, then we are going to have one force going up like so, because it's the one that has remained there, right? One has been converted with the other one into a couple moment. So we have a 5 pounds, and then we have a couple moment which is a 5 by 5, which is 25, and it's anti-clockwise, which is our conversion for positive, like so. Okay, and this is a 25 pounds feet. Okay, and this is point A. And then when we get to force number 2, when you look at this again, we realize that we are going to have of course we do have these two opposing forces at A, but then we are saying let's leave those that the original and the other one that is in the opposite direction, like we did in the first case, the original and the opposite direction. So we are going to leave this one, we are going to leave this one, and we assume that this and this is supposed to create a couple moment. But since these are in the same line, they are collinear, we do not have, or the perpendicular distance between them is 0, right? Therefore, there is not going to be any couple moment. So these two are just going to cancel, this one and this one, right? Or you can also think of a force having that property of transmissibility along its line of action, right? So what we can just remain here with is just this particular force, this one here, right? And it's going in this direction like this. And this is equal to 10 feet. 10 pounds. So when we've done this, then it means we have worked out the problem, right? We've worked out the problem. So we have 5 feet, we have 10 feet. So what we've done here is we've written this particular force system into an equivalent resultant force, F resultant, which is just equal to F resultant in the x direction is 10, F resultant in the y direction is 5, and the resultant of the two using Pythagoras theorem, where is my calculator, which we can calculate, we can say is equal to 10 squared plus 5 squared, then root of that gives us 11.18. So we have the resultant. We can write this now with the resultant. We have the resultant force. Let's put it here, somewhere here. We have the resultant force, and it's going to be in between these particular forces. So let's write it in green. It's going to be in this direction like this. So this is the resultant force. This is the resultant force, and this resultant force is equal to 11.18 if we just rounded it off up to there. So let's find this angle theta. So theta, this is 11 point, we said this is 11.18, okay, using Pythagoras. And if we calculated this angle, we have the change in y, which is 5, divided by the change in x. So this gives us, grab your calculator, 5 divided by 10, tan inverse of that gives us a 26.57. So this is equal to 26.57 degrees. And then we have a moment, a resultant moment. We have the resultant moment here, which is m resultant, which is equal to a positive value, which is equal to 25 pounds feet, which we can indicate here like this. Okay, at about point A. So we'll have summarized the equivalent resultant force and couple moment acting at point A. So the effect on this particular beam for our example problem is the effect in terms of resultant force and the resultant couple moment acting at point A is the same compared to the original structure. So this is basically what we're going to be doing, right? So we can either use the method where you have perpendicular distance between two forces in the opposite direction with a similar magnitude, or we can take the moments or calculate the moments about a given point, okay, like we've always done in other cases. Remember, we were solving couple moments using two methods, where you have one method taking moments about a point, or summing up the couple moments, it still gives us the same answer. So I did want to talk about this briefly so that when we start solving this particular problem, we are going to move a little bit faster. I hope this has provided some insight on what we are going to be basically doing. Okay. All right, let's wrap this so that we solve the problem. Okay, so what do we need to do here? We have the reference. Our reference is A. So this is where we need the forces. So now let's identify the slope for this the first 100. This is 3, this is 4, and then the hypotenuse there becomes 5. So we'll have components here. We'll have this one, which will just be 100 by 3 divided by 5. This is therefore going to be equal to 60, right? 5 into 20, 5 into 100 is 20. 20 by 3 is 60. And then we have another one, we have another force, which is this one here. This is just 100 by 4, the rise divided by 5. 5 into 100 is 20. 20 by 4 is 80. All right. So now we are going to sum up these forces in the x and in the y and taking moments about point A. So we'll say summation of forces in the x direction equal to, this is going to be equal to, what do we have? In the x we have a 60 is positive minus 200. If we subtracted this, it gives us, what does it give us? It gives us a 140, right? 140. And then we have summation of forces in the y direction equal to, going up in our reference, we have 80, and then we have minus 150. What do we have? 80 minus 150. This 140 is minus here, sorry, I'm supposed to indicate that. So this one gives us a minus 70, right? Yes. Then let's take moments, summation of moments about point A, which is similar to summing up the couple moments, right? We did that in the other example. It's the same thing. There we summed up the couple moments. So let's take moments about point A due to all these forces. So 150 will give us a negative clockwise moment. 150 by 3, the lever arm. 200 will not give us any moment because the lever arm is equal to 0. And then we have 80. 80 is giving us a positive moment, which is 80 by 6. And then 100 is giving us a negative 60 is giving us a negative moment, which is 60 by the lever arm 4. So if we are to sum up all these, it gives us minus 150 by 3 plus 80 by 6 minus 60 by 4. We have a minus 210. All right. So this is our initial resultant force in terms of x and y. But we can further simplify these particular forces. Let me draw them so that you see how they look before we simplify them. So if we have a beam like this, and then like so, so what we are saying is, if this point is our A, so what we are saying is, we have a force here in this direction, which is equal to 140. Then we have another force going down, which is equal to 70. Then we have a clockwise moment, okay, which is equal to 10. But we can simplify this further by working out 140 and 70 using Pythagoras, so that we have the force resultant is equal to root of minus 70 squared plus minus 140 squared. So if we were to work out this, we have 156.52. So if we are to write this once more again, something like this, and there let's say it's bent like this. Of course this point is A. Let me just indicate it. We have this point which is A. So we'll have the resultant force. Let me finish this. Let's also calculate the angle. The angle itself is equal to tan inverse change in y, which is 70, yes, divided by change in x, which is just for 140. This gives us 70 divided by 140. Of course both of them are negative, right? So they cancel each other out. Then we'll have a 26.57 degrees. So if we are to write this, we'll have the resultant, let's say like this. We'll have the resultant like that. Okay, we'll have the resultant like that, and then this is the angle. This is the angle that we just calculated. It is this angle here, right? It is this angle here. Let me write it in blue. This is the angle that we just calculated. Remember, opposite over hypotenuse. So this one is a 26.57 degrees, and this value here we said is a 156.52 pounds, and then we have a moment which still maintains, and this moment is clockwise, and this magnitude is 210, which is a couple moment, of course, acting at point A, 210 pounds feet. Right. So this is really about it. This is really about it. This one we have an equivalent here. We have an equivalent. So an equivalent resultant force, which is equal to FRR equal to 156.52 pounds, and this is the resultant, of course, we've shown it. And then we have the angle itself, which is just calculated, and we've shown it also, a 26.57, and then we have the moment, resultant moment, which is equal to, so on this we have that angle, that resultant, and then we have this is equal to 210 pounds feet. Yes, and then this we are measuring it with reference to the negative axis, right? So this is about it. This is really about it, and I hope the video was helpful, and if it was, give me a thumbs up, like my video, continue subscribing and liking my channel. Bye bye, and see you in my next screen.